This video will cover analog-to-analog conversion, a crucial topic in analog transmission. Analog-to-analog conversion is the process of representing analog information using an analog signal. It's essential for long-distance transmission, converting the message into a modulated carrier, and utilizing high-frequency signals. Analog modulation is necessary for several reasons. It enables efficient transmission because higher frequencies travel better over distance. It also allows multiplexing, where multiple signals share a single channel. Additionally, it helps reduce antenna size and improves noise resistance. The basic idea of modulation is defined by the equation. Modulation equals message plus carrier. The message or baseband signal modifies one or more characteristics of the high-frequency carrier signal. The message signal is the original low-frequency information, such as voice, music, or low-res video. It contains the actual intelligence and is also known as the modulating signal. It oscillates at frequencies much lower than the carrier bandwidth. The carrier signal is a high-frequency sine wave that transports the message. It is defined by the equation T equals AC cos 2 pi FCT plus phi, where AC is the amplitude, FC is the frequency, and phi is the phase. The carrier signal has three key parameters that can be modulated: amplitude, which is the peak value of the wave; frequency, which is the number of cycles per second; and phase, which is the position within a cycle. Modulation is formally defined as the process of varying one or more properties of a periodic waveform, the carrier, with a modulating signal that contains the information to be transmitted. There are three primary modulation types. Amplitude modulation, or AM, varies the voltage peak. Frequency modulation, FM, varies the rate of cycles. Phase modulation, PM, varies the timing shift. In amplitude modulation, the carrier signal's amplitude changes in proportion to the message signal's instantaneous amplitude. When the message signal increases, the carrier envelope expands, and when it decreases, the envelope contracts. AM characteristics include constant frequency and phase, while power varies with the modulation depth. The visual representation shows how the message signal dictates the amplitude variations of the carrier. The AM wave equation is S of t equals AC1 plus MT cos 2 pi FCT, where AC is the carrier amplitude and MT is the normalized message signal. An AM signal consists of three components: the carrier, which is the central frequency spike, the upper sideband USB at FC plus FM, and the lower sideband LSB at FC FM. The carrier in AM carries no information and consumes substantial power, up to 66%. However, it is necessary for simple demodulation. This leads to power inefficiency, as most power is wasted on the carrier rather than the information-rich sidebands. The sidebands are created as sum and difference frequencies between the carrier and modulating signals. USB and LSB are mirror images, and they contain all the message intelligence, such as voice or data. The upper sideband, or USB, is defined by the carrier frequency plus the message frequency, represented as FC plus FM. This defines the upper frequency range of the transmitted signal. The lower sideband, LSB, is defined by the carrier frequency minus the message frequency, represented as FCFM. This defines the lower frequency range. The modulation index, represented by M, is the ratio of the message amplitude to the carrier amplitude, or AM divided by AC. It dictates the depth of modulation. The index is important for signal quality, as a higher M increases the signal-to-noise ratio, or SNR. It also improves power efficiency by increasing the useful sideband power. Undermodulation occurs when the index M is less than 1. This results in a stable but weak signal, where the envelope never touches the zero line. Transmission is safe, but inefficient. Perfect modulation occurs when the index M equals 1. This is the optimal performance, providing maximum power in the sidebands without distortion, which is ideal for broadcasting. Overmodulation occurs when M is greater than 1. This causes signal distortion because the envelope crosses zero, leading to phase reversal and clipped audio output. The bandwidth of an AM signal is calculated as twice the highest frequency in the modulating signal, or 2 times FM max. Advantages of AM include simplicity, making transmitters and receivers inexpensive and easy to build. Additionally, demodulation is simple, often requiring only a diode envelope detector. Disadvantages of AM include low noise immunity, as static and atmospheric noise directly affect the amplitude. Furthermore, efficiency is low, as most power is in the redundant carrier. AM is commonly applied in AM radio for long-range broadcasting on MW and LW bands. Aviation uses AM for air traffic control due to its robust behavior during signal fades. In frequency modulation, or FM, the carrier signal's frequency is varied in proportion to the message signal's amplitude. Higher message voltage equals a higher carrier frequency, and vice versa. FM characteristics include a constant amplitude, meaning the peak voltage remains identical. It also offers good noise resistance because FM receivers ignore amplitude variations where noise typically resides. The FM equation is S of t equals AC cos 2 pi FCT plus MF sine 2 pi FMT. AC is the carrier amplitude, FC is the carrier frequency, and MF is the modulation index. Frequency deviation, represented by delta F, is the maximum difference between the modulated frequency and the carrier frequency. It determines how far the carrier frequency swings from its center value. The modulation index for FM, represented by beta, is the ratio of the frequency deviation to the maximum message frequency. It determines the number of significant sideband. The bandwidth of FM is theoretically infinite, but practically concentrated. It is much larger than AM bandwidth and depends on both the frequency deviation and the modulation index. Carson's rule provides a practical approximation for the required bandwidth of high-fidelity FM signals. It is an industry standard for calculating FM bandwidth. Advantages of FM include high-fidelity audio due to a wider frequency range and superior signal-to-noise ratio. The capture effect allows the receiver to lock onto the strongest signal, rejecting interference. Disadvantages of FM include the use of more spectral space, requiring a much larger bandwidth, such as 200 kHz per station. It also requires more complex circuits, including precise frequency discriminators and PLL circuits. FM is widely applied in FM broadcasting for high-quality music and voice radio. It is also used for TV audio, as the sound component of analog TV signals is FM modulated.